Let us look at integral calculus, a historical perspective. See, one of the problems that they addressed, mathematicians of those times, was finding the area of a circle. Eudoxus, around 400 BC, described the method of exhaustion for finding the areas of curved figures by inscribing and circumscribing polygons or polygonal solids, depending if it is a sphere, polygonal solid. If it is a circle, polygons. Now, how does that work? That method of exhaustion. Basically, you draw a polygon, a regular polygon inside the circle. Then the area of this polygon will approximate the area of this circle. Not a very good approximation, right? Lot of areas between the area of the circle and the area of the square. So now what we do? We increase the number of sides of the polygon. So we inscribe a hexagon. Now what has happened? The gap between the polygon and the circle, the difference in the areas has reduced. Again, we increase the number of sides of the polygon. Now we have 8 sides. So we have reduced the difference between the area of the circle and the polygon. We keep doing it. Till when? Till the difference between the circle and the area of the polygon has been exhausted, or till basically you get exhausted drawing all these polygons. So this was the method of exhaustion. Euclid, around 2300 BC, used the method of exhaustion to prove that for given two circles C1 and C2, area of C1 is to area of C2 is equal to the ratio between the squares of their diameters. So he basically looked at ratios. And this he described in Euclid's Elements, book 12, proposition 2. And around 2200 BC, Archimedes came along. He showed that the area of any circle is equal to a right-angled triangle in which one of the sides about the right angle is equal to the radius and the other to the circumference of the circle. And he also used the method of exhaustion. This he describes it in Measurement of a Circle, proposition 1. Okay, so let's see how visually the areas were being calculated. So let's reduce the number of sides. Let's start with a square being inscribed. You break it up into triangles because the area of the triangle was easy to calculate. Remember, the moment we go to the next polygon of 6 sides, we don't have a square. So we can't use the area of a square. But triangles we can use with respect to any number of sides in the inscribed polygon. So now you have 4 triangles, calculate the areas of the triangles and sum it up. Now let's increase the number of sides. Again, you have this. Again. So it's just a question of calculating areas of triangles and summing it up. How does this look in modern notation? Now, the sum of these triangles will give you the exact value for the area of the polygon. So this summation notation, you're already familiar with. Sum of all the triangles, areas of the triangles from 1 to n. So here I have 14 triangles. So 14 times we calculate this and sum it up. Now, to really make it a better and better approximation, what do? We keep increasing the number of sides of the polygon. So we keep increasing the number of sides. So we end up with the area of the circle in the limit n going to infinity of summation k equal to 1 to n of 1 by 2 times base into height. Now, of course, remember Archimedes and Euclid, they didn't know these notations. Here, I'm showing it to you for your understanding, how all this flows from the method of exhaustion. Now, why are we not using k in the expression? Because k takes us through these triangles one by one. And all these triangles have the same base, that means equal base, and they have equal heights. So we don't really have to be specific to a particular triangle when it comes to base and height. We can take the base and height of a single triangle and repeat it. Now, to get the area of the circle, we have to keep increasing the number of sides of the polygon. Numerically, if you want to see, then this is the area of the polygon by doing this summation. And this is the area of the circle. Now let's start from the beginning. Area of the polygon is 18. Area of the circle is 28.27 dot 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 dot. So not a very good approximation. But if we take it to a hexagon, what happens? A much better approximation. 23.38, 28.27. Let's take it to octagon, decagon, 12 sides, 14, 16, 18, 20 sides. Not bad, right? If we take it to say 200 sides, then we get this 28.269, 28.274. So if we do rounding, we will get 28.27, 28.27. 2 decimal places. Very interesting, right? So I think that's enough for this session. In the next session, we will take up the introduction from a modern perspective. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.